Hey guys, hope everybody's doing well. I'm Dr. D. Today we're going to keep working on numerical summary measures. Last place we left off, we were talking about, what were we talking about? We're talking about central location and non-central location. And today, now that we've finished that, we're going to start embarking on the process of talking about dispersion. Right? Dispersion is the spread outness of our data, which is not a word, but you know what I mean. The spread outness, right? How dispersed it is. And dispersion is what makes the world an interesting place. It's what makes it important to think about statistics, right? If everything was the same, there would be nothing to explain. But what we really want to explain is why things are different. And in order to do that, we need to talk about how things are different, right? How different they are, and then how much of that we can hope to explain. This is going to be a very short video because I just want to talk about the two easiest measures of dispersion that we have. One is the range, and the range is the simplest measure of dispersion. It's just the maximum value of x minus the minimum value of x. And so, for example, if we have this data set that I just popped in here, then our maximum value of x is 63, and our minimum value of x is 44, and 63 minus 44 is 19, and so that's our range. Now, range has one big advantage, which is it's super easy to calculate. Another advantage is that it tells you what values x does take or could possibly take in your data set. And so range is really useful when, for example, you want to label your axes. If you want to have x on this axis, well, then you know that you're going to need to cover 19 units here, even if you truncate this axis, right? You still need to have those 19 units. The problem with range is that it's very susceptible to changes in the edges, right? So if this went from 63 to 163, then the range would go up to 119, even though the level of dispersion in our data set hasn't changed that much. I mean, one of them got really strange, but it could just be an error, right? It could just be measurement error. Somebody typed in the wrong number. 163 degrees, I don't think there's a place on Earth that gets that hot very often. Maybe there is, I don't know. I'm skeptical, but I could be, I totally could. I keep thinking, Sahara, maybe, I don't know. It's possible. It seems unlikely. Certainly not if the rest of the places in the data set are in the 40s, 50s, and 60s. So in order to solve that problem, one measure that we use, another simple measure that we use, is the interquartile range. Maybe I'll write it all the way out. Interquartile range. And instead of looking at the full data set, the interquartile range looks at the distance between the third quartile and the first quartile. Cool. And so in order to calculate the IQR, we need to calculate these, which takes a little bit more work. So Q3, that's the 75th percentile. And the 75th percentile for this data, well, to find that, we need to find the rank of the percentile first, and R is equal to P over 100 times N, where P is this number, and N is our number of samples, or a number of observations. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if N equals 15 and P equals 75, then this is going to be 75 over 100 times 15, which is 11.25. I know that because I just did it not long ago. But it's 3/4 times 15, which is 45 divided by 4, which is 11.25. Now, once we have our rank, the way we decided that we would deal with decimals in our rank is just to round them up. So this becomes 12, and our 12th number, 15, 14, 13, 12, is 58. So Q3 equals 58. 58 puts 3/4 of our data less than or equal to it, and 1/4 of our data greater than or equal to it. And so that's a solid number there. How about Q1? Well, Q1 is going to be our 25th percentile. And so in this case, our rank is going to be 25 over 100 times 15, which is going to be 1/4 times 15, or 15 over 4. 15 over 4 is going to be, what is that? That's 3.75, 3 3/4. Now we round that up to 4, and we have 1, 2, 3, 4. Right? We're on the 54 is Q1. So Q1 equals 54. So in this case, our interquartile range is going to be 58 minus 54, which equals 4. Right? Now, range and IQR are always not going to be comparable, right? Really, we compare the range of one data set to the range of another data set, and the IQR of one data set to the IQR of the other data set. Because the range, by definition, is going to have less variation, right? It's pulling in, right? If range takes the two tails, Q3 deals with a much, thinner slice of the distribution. But range IQR has the advantage that it doesn't. It's not nearly as susceptible to changes in these outlying measurements, right? So if this goes to 163, then our range goes to 119, but our IQR does not change, right? And that's a good thing because it's more stable, it's more robust, right? But it's a bad thing because the variation, the dispersion has changed. It hasn't changed by as much as the range would have you believe, but it's changed by a lot more than 0. And so it would be nice for us to be able to come up with some other measures of dispersion that capture a little bit more, in more detail, what's going on with our data. And so in the next video, I'm going to talk about standard deviation and variance and how those capture dispersion a little bit more directly. Thanks, guys. See you soon. Bye.